architecture for everyone. This is something that's very, very dear to my heart. So the origin of this talk is kind of interesting. Way back towards the end of last year, I was speaking to a friend who was looking for a new job, and they showed me one of the job specifications that they were handed. And this was like a regular kind of front-end focused web devy job. And on the job spec, there was basically a whole bunch of jargony rubbish around how you would have to be able to design architectures for web applications, for how you were going to run your hosting, all this stuff. And I sat there reading it thinking, why on earth would anyone ever expect, firstly, your average web dev to know any of this stuff? And secondly, why would you expect anyone to even know the words? And, you know, they were a little bit flustered at the concept, because as they were reading down this job spec, the question was just like, I literally do not understand what any of this means. So I thought, you know what, like, architecture is full of garbage, and it's full of junk, and it's full of ways that people have made things seem very, very complicated over time. So what I want to do is I want to explain what all the words mean from the very, very top of the web stack all the way to the very, very bottom, and kind of tell you what to expect when you see some of these buzzwords and pieces of jargon thrown out there. Okay, so first I'll introduce myself. So I'm David, and I'm an independent software consultant from London in the UK. I work for myself, mostly doing mentoring and strategic work for big UK dot-coms. So I've had a wide variety of jobs with variably pretentious job titles like head of engineering, chief technical architect, head principal, which all sounds a lot fancier than it really is. I just love making things, and I love the people that make things, and I try and spend some time helping them do that a little bit better. I also wrote a couple of kids' books about programming in JavaScript. That's my one plug, available in all good bookstores, Get Coding 1 and 2. I'll never make a good advertiser. So, someone said the dreaded architecture word, and you're not an architect. You're scared when someone challenges your understanding of computational complexity when all you're trying to do is put a widget on a web page. Never fear. It's probably not as sophisticated or complicated as you might think. So architecture has this reputation for being unapproachable, gate-kept, and air quotes hard computer science. And most of the software architecture you run into for your average to web scale apps is astonishingly similar. So we're going to cover the basics, some jargon, some architectural patterns that you'll probably see everywhere, and we're going to do it in this architectural primer for non-architects and web programmers. Okay, so let's start at the very, very beginning, the basics. The web, or the World Wide Web, to use its hilariously antiquated, full honorific, is just really a load of computers connected to the internet. Right? So the web is a series of conventions that describe how resources, when you hear that just think web pages, can be retrieved from these connected computers. So the long story short is that web servers implement the HTTP protocol, which is just a series of commands that you can send to remote computers that let you say, hey, computer, send me that document. Right? So if this sounds familiar, it's because literally that's what your web browser does when it works. It's nothing more than that. So when you type in www.myawesomewebsite.com into your browser, the code running on your computer crafts a HTTP request and sends it to a web server associated with a URL, read website address, that you typed into the address bar. So then the web server, which is nothing more than a program running on another computer that is connected to the internet, that's listening for requests and returning data when it receives them. So the fact this all works at all is a small miracle, and it's built on top of DNS. Okay, so if the slides are pixelated, what we're going to do is we're going to take my face away, and we're going to replace it with the screen share, because that'll be better. Bam. Is that better? Amazing. Yeah, I think webcams and screen shares are optimized differently. No problem. So yes, the fact that any of this works is built on top of DNS. So all DNS is the thing, it's basically a phone book for the internet. It's the thing that turns the string, myawesomewebsite.com, into an IP address. And then there's some networking, routing, and switching underneath that helps your data packets move between those two computers. You probably don't need to know too much about any of that in real terms unless you're going to become a network engineer professionally. So there's a ton of general purpose web servers out there, but realistically, you're probably just going to see a mixture of Apache, Nginx, and Microsoft IIS, along with some development stack specific web servers. So for instance, there's a trend in the the mid 2010s onwards where Node.js serves itself, ASP.NET Core for C# serves itself, HTTP 4K for Kotlin serves itself. They're all web servers. And if you've done any web programming at all, you're likely to be at least a little bit familiar with HTTP. So HTTP stands for the Hypertext Transfer Protocol, and that's what your browser talks when it talks to web servers. So let's firstly take a look at this raw HTTP message. Okay, so all the basics of HTTP are pretty easy to grasp. There's a mandatory request line, and that's the first bit with the verb where it says get, and that can be one of get, post, put, and head most frequently. Most people normally see get and post. And then there's the URL, which is the web address, and the protocol version, in this case, HTTP 1.1. There's then a bunch of optional request header fields, and that's basically all the other stuff in the request. Think of this as extra information that you're handing to the web server that's about you. And after your headers, there's a blank line and then an optional body. That's basically HTTP 1.1 in its simplest possible form. It's just some text that we send to another program running on another computer. So the server will then respond in a similar form. So the first line being a status code, followed by headers and a response body. The web server, based on the content of the request, can send you anything it likes, really, and the software that's making the request must be able to interpret that response. There's a lot of nuance in asking for the right thing and responding appropriately, but the basics are all the same. So the web is an implementation of the design pattern REST, which is a much mentioned buzzword, which stands for representational state transfer. You'll hear a lot of people talk about REST, and you'll hear them talk about it a lot. So it was originally defined by a man called Roy Fielding in his PhD dissertation. But more importantly, what it was a description of the way HTTP 1.0 worked at the time. And it was documented and described at the same time Fielding was working on the spec for HTTP 1.1 himself. So REST is the web. The short version, very, very simply, is uniquely addressable URIs, so web addresses, that return a representation of some sort of state held on a machine somewhere else. So that representation of state could be a web page, it could be a document, it could be an image, it could really be anything. Depending on what the client asks for, the representation of that state could vary. So I could ask you for a representation of, say, you. You have a URL, me, David. But if I ask you for an image, it could return a photo of my face. If I ask you for text, it could return a description of me. That's the basics of REST. It's a representation of some resource. So what we've done is we've described HTTP, how the internet talks to each other. We've described REST. And actually, this is an architectural style. So you can write good software following plenty of different architectural styles and architectural patterns, but most people stick to a handful of common patterns. So I can guarantee some of you will have seen some of this stuff before. So MVC. MVC stands for Model View Controller. It's a very, very simple design pattern that decouples the processing logic of an application, the stuff that's in your controller, from the presentation of it. So like MVC was really catapulted into the spotlight by the success of Ruby on Rails in the late 2000s, although the pattern itself, interestingly, was a couple of decades older. And when most people say MVC, what they're normally describing is a Rails-style MVC app where your code is organized into a few different folders on your disk. So you will literally have a folder for controllers where logic tends to live, lots of people will argue that you have to put logic somewhere else, but application logic and controllers and the thing that controllers calls. Models is the data that you're going to use to present on the web, and then the views is just the logic you're going to use to write some stuff onto the screen in HTML that uses the data in your model. That's MVC, that's the whole pattern. So as a broad generalization, when you look at these Rails-like apps, by default, if you have a URL that looks something like, that, mycoolsite/home/index, an MVC framework using what it calls roots, those are just rules that define where things are looked up. We'll try and find a home controller by using the word home in the URL. What that means is it'll look for a file on your disk called homecontroller.ruby or .cs if it's a C# application, or JS, it's a JavaScript application, inside the directory controllers. And then it would try and find a function called index that would probably exist. That function would probably return a model, some data to be rendered by your view. And the view itself is just a HTML template inside the view folder. So all the different frameworks do this in slightly different ways, but the core idea stays the same. Features grouped together by controllers with functions that just return pages of data and views that handle input from the web. That's the pattern. So one of the other common patterns you'll see the single page application with an API. So SPAs are incredibly common in post-2015 version of the world. They've been popularized by client-side web app frameworks like Angular, React, and Vue.js, with the only real difference here being that we're taking our MVC app and shifting most of the work it does to the client side. So there are a couple of different flavors here. There's client-side MVC, where you see that same model view controllers kind of pattern. There's Mvvm, model view model, and there's FRP, functional reactive programming. So FRP, for instance, is what React is. So React is an implementation of functional reactive programming on the web, where you have functions that react to some kind of state change. The differences might seem quite subtle at first, though. So Angular is a client-side MVC framework. It follows the model views and controllers pattern, except now it's running inside your user's web browser, not on your web server. React, being an FRP implementation, is a little bit more flexible, and it's concerned with state change events in data, often using some kind of event store like Redux. Mvvm is equally common in single-page apps, when there's two-way bindings between something that provides data, the model, and the UI, which the view model serves. So it's all about managing the interactions back and forth between this model and the UI that reacts to it. Underneath all these client-heavy JavaScript frameworks is generally an API that looks nearly indistinguishable from the MVC app in the last slide. But instead of returning pre-rendered pages as views, it just returns the data that the client binds in its UI to. So it's just kind of CV, I guess. Just sorry, MC rather. So perhaps the outlier of the set. There's been a resurgence of static websites in the 20-teens. So scaling websites for high traffic is really hard when you're running code on your computers. Like, we spent years building relatively complicated and poorly performing content management systems like WordPress that cost a lot of money and hardware to scale. These things are really, really difficult. As a reaction, moving the rendering of content to development time as an exercise has distinct cost and scalability benefits. Like, literally, if you have no code running on a computer, then it can't crash, right? Simple. So static site generators have become increasingly popular, and all they really do is they take all the logic that would normally happen when someone calls your server and asks for a page, and they put it in your build process. So you basically run that request for every possible page, generate the output, and put it somewhere. So what they do is they normally allow you to use your normal front-end web development stack, but then generating all the files at build time, you bundle and distribute them to someone else's web servers. And these other web servers are called CDNs, content distribution networks. So again, these are just really, really jargony names for someone else's web server that doesn't run your logic, it just serves your static files. That's all a CDN is. Some of them are clever and copy files to places closer to different geographic regions. So there are tools like Gatsby, Hugo, Jekyll, YM that all do this kind of stuff. And actually what we're seeing these days is we're seeing a rise in static hosting focused service offerings from vendors. So Microsoft Azure static web applications, which is a mouthful, Vercel, all these kinds of things are built to host static content. There are other archetypes that web apps follow. There's this slowly rising trend in transpiled frameworks. So when I say that, what I mean is Blazor in C#, where it takes C# and compiles it to WebAssembly to run in your browser, and Kotlin has a JavaScript compile target that does the same thing. But the vast popularity of the dominant JavaScript frameworks of the day means that they really all have to play along nicely, and the survival of frameworks like Blazor and Kotlin is entirely dependent on how well they get their native JavaScript interop done right now. So why would I choose one of these architectural patterns over the other? Right, why? Well, it's a tricky question, and here's the thing that people basically won't tell you. Honestly, for the most part, it's just a matter of taste, and they are all perfectly appropriate ways to build web applications. Like, they're all the right answer, honestly. So server-rendered MVC apps are really good for low interactivity websites, but kind of cruddy, lots of data access, right? Even though high fidelity front end is a growing trend, there's a huge category of websites that are just websites, right? Not web applications that require rich user interactivity. They're just websites. And actually the complexity cost of the large tool chain from front-end heavy websites is often not worth the investment, and just rendering some stuff on the server is totally fine. By contrast, anything that requires high fidelity user experience, almost the default now in a lot of very, very consumer facing stuff, is probably going to be a React, Angular, or a Vue app. That's what it's going to be, like, really realistically. The programming models work well for responsive user experiences, and if you don't use them, you'll mostly end up reinventing most of these things yourself. Like the number of projects I've seen where people have gone no framework, vanilla JavaScript, and then basically built their own rubbish version of Angular is surprisingly high. So then let's think about static sites. So static sites are great for blogs, marketing microsites, content management systems, anything where the actual content is the most valuable interaction. And the reason for this is because they scale really well. They basically can't crash, and they're really, really cheap to run. So then let's talk about this stuff, right? HTTP APIs, REST, GraphQL, backend for front ends. Okay, so the reason we're talking about all this is you're absolutely going to end up interacting with some APIs. And there's a lot of terms that get thrown around to make this stuff sound complicated. The core of it is really, really simple. Most web APIs you use or build are going to be REST-ish, right? And what I mean by that is you'll be issuing some kind of HTTP request, similar in the way that your browsers do. They will mostly probably return some JSON, a JavaScript blob of data, though sometimes maybe XML. And it's safe to describe most of these APIs as JSON RPC, remote procedure call, or XML RPC. The reason there's a little bit of difference there is, REST means something, and most of the APIs you see in the world aren't actually REST APIs. They're just data you get over HTTP, and that's kind of fine. So back at the turn of the millennium, there was this push for the standardization of SOAP, which stands for Simple Object Access Protocol. And a lot of people are down on SOAP because it's very, very high ceremony. The request's very big. And SOAP came with a lot of good stuff, but people found this XML data cumbersome to read, and so they diminished in popularity. So ironically, lots of the stuff that was solved in SOAP, problems like consistent message envelope formats, security, schema validation, has subsequently had to be resolved on top of JSON using emerging open-ish standards like Swagger, which is now called OpenAPI, and JSON API. So we're very, very good at reinventing things we already had on the web. And a lot of the place that APIs live now and a lot of the technology we use basically looks like SOAP did in about 2002. So what makes a REST API and not JSON RPC? Well, I'm glad you didn't ask. So REST at its core is about modeling operations that happen to the resources over HTTP. There's a really great book by a guy called Jim Weber called REST in Practice that came out in about 2011, I think. And if you want to deep dive into why REST is a good architectural style, and it is, there's a lot of modern naysaying about REST. And it's relatively uninformed and not too dissimilar to the way that SOAP got a lot of naysaying in an uninformed way before it, ironically. So people really, really care about what is and isn't REST. And you'll probably upset people who really, really care about REST by describing JSON RPC as REST. So this is a very, very complex looking diagram. So JSON RPC is at level 0 on this model, which is called the Richardson maturity model. And it's a model that describes the different qualities of RESTful design. I suggest you look this up later. We're not going to dive deep into it. But the fundamental difference is at the very, very top of this model, we've got this concept of hypermedia and the wonderful acronym like peak jargon, hypertext is the engine of application state, HATIOS. Basically, it just means that when you get responses from an API, inside the response, it will give you a bunch of links telling you what you can do next with that data. Much like when you request a web page, there will be links on the web page telling you where you can go next. So it's about modeling of those interactions. But don't worry too much about it because you can just build REST-ish, right? Sane, decent JSON RPC by doing a few things. First, you need to make sure you use HTTP verbs correctly. So just use get for fetching data and never with side effects. And use post when you're doing something, when you're doing operations, changing state. And then use put when you're creating stuff, but the state is controlled by the client. Cool. So after that, make sure you organize your APIs into some logical resources, just like your core domain concepts like customer, product, catalog. And then finally, use correct HTTP response codes for people that are interacting with your API. So you might not be using hypermedia as the engine of application state at this point, but that'll probably do well enough and literally nobody will come for your blood, like it'll be fine. You'll also get a lot of the benefits of a fully RESTful API by doing just enough. Like resources will be navigable over HTTP. Your documents will be cacheable. Your API will work with most common tools, right? You'll be able to use Swagger or an open API library to generate a schema, and you're pretty much doing what most people are doing at that stage. So yeah, like I read on Hacker News that like REST sucks and GraphQL is the way to go, yeah? Yeah, like we all read that post. Right, cool. So GraphQL is confusingly a query language, a standard for HTTP APIs, and a schema tool all at once with the same name, just to make it really easy to understand. So with the proliferation of client-side heavy web apps, GraphQL has gained popularity by effectively pushing the definition of what data should be returned to the client into the client code itself. So it's not the first time these kinds of query from the front end kind of approaches have been suggested. And it likely will definitely not be the last. So what sets GraphQL apart a little from previous approaches, notably Microsoft's OData, which was kind of the same thing, is the idea that types and queries are implemented with what they call resolvers on the server side. So rather than just anything you do in your browser being run against your database, anything you do in your browser is mapped to a query which runs code against your database. And that subtle piece of indirection protects you a little bit, right? So it's useful for a couple of reasons. It means that GraphQL can be a single API over a bunch of disparate APIs in your domain. It can solve the overfetching problem that's quite common in REST APIs by allowing the client to specify just the narrowest subset of data that they need. And it also acts as like an anti-corruption layer of sorts, preventing unbounded access to databases or horrible things that you could do to your downstream systems, right? So GraphQL is also designed to be this wonderful single point of connection that your web or mobile app talks to, which is really useful for optimizing performance. Simply, it's quicker to call one API over the wire and then have that call downstream APIs with the lower latency that involves than your mobile app calling at high latency all of those other APIs itself. It's just a little bit faster. So GraphQL really is just a smart and effective way to schema your APIs and provide a BFF. That's backend for front end, not a best friend forever, right? And this is a BFF that's quick to change. So what on earth's a BFF? Like cool. I keep on reading about BFFs. Right, so imagine the problem. You're working for Megacorp, where there are hundreds of teams or squads you don't really remember because they rename the nomenclature every other week. Each is responsible for a set of microservices. You're a web programmer. You're trying to get some work done, and a new feature has just launched. So you cool. You go and read the docs. And the docs describe how you have to orchestrate calls between several APIs that all require OAuth tokens and claims, and eventually then you'll have your shiny new feature. So you write the API calls, and then you realize that the time it takes to keep sending data to and from the client, let alone the security risks of having to check all of the data is safe for transit, slows you down to a halt. So exactly this is why you need a best friend forever. Sorry, backend for front end. So what it does is it gives you an API that serves one and specifically only one application, right? So it translates an internal domain, Megacorp business domain, into the internal language of the application that it serves. It takes care of things like authentication, rate limiting, stuff you don't want to do more than once. It reduces needless round trips to the server, and it often translates data from some internal representation to a representation a little bit more suitable for the application that uses it. Think of it as an API, but just for your app that you control. And tools like GraphQL and OData are excellent for BFFs. So GraphQL is especially good when combined with modern JavaScript tools, and along with libraries like Apollo and Apollo Server. And what they do is they help optimize these calls for you by automatically batching stuff together. It's also really front-end dev friendly because queries and schemas strongly resemble JSON. So it keeps your stack kind of JavaScript all the way down without being beholden to some distant platform or backend team, right? Like these are really, really powerful. And actually, you can think of them as if you had an MVC app, it's all the logic that would traditionally be in the app, pretty much. So now we understood web servers and web apps and APIs. Surely there's more to modern web programming than that, right? So I'm going to go through a couple of other things you might run into most often. Okay, load balancing. Let's talk about load balancers. So if you're lucky enough to have traffic to your site, but unlucky enough to not be using as a platform as a service provider, more on that later, you're going to run into a load balancer at some point. Please do not panic. So load balancers talk an archaic language and are often operated by grumpy sysops people, or are really just running copies of Nginx, right? So all a load balancer really does is accept a HTTP request for your application or from it, and then pick a server that isn't very busy and forwards the request to it. So a load balancer gives you a way to run lots and lots of copies of your program so that when someone requests data from it, the server that is most free at the time can respond. You can make load balancers do all sorts of utterly insane things that you probably shouldn't use load balancers for. People will still try. You might see load balancers load balancing a particularly hot path, for instance, in your software. So say your checkout might get load balanced to a dedicated pool of hardware to try and keep it safe or isolate it from failure. You might also see load balancers used to take care of SSL certificates for you. They call this SSL termination. And what that means is when you have to put an SSL or TLS certificate on your web app, all your web servers behind the load balancer just talk plain HTTP, and then your load balancer deals with the HTTPS traffic encryption. That's all SSL termination means. So let's talk about distributed caching, right? So if one computer can store some data in memory, then lots of computers can store, well, a lot more data, right? So distributed caching was pioneered by a program called Memcached. This was originally written to scale the blogging platform LiveJournal in 2003. And at the same time, Memcache helped LiveJournal share cached copies of all their latest blog entries across a relatively small number of servers, and it vastly reduced the database server load on the same hardware. Interestingly, it won like an award in like 2004 as like the biggest scalability thing in the world at the time. So memory caches are used to store the results of something that is heavy to calculate, that takes time, or just needs to be consistent across all of the different computers running your software. So in exchange for that little bit of network latency and getting the data from a memory cache, it makes the total amount of memory available to your application the same as the total amount of memory on all of your web servers. So if you have 3 web servers with 1 GB of RAM, what that means is each copy of your program running on each of those servers actually have access to 3 GB of RAM, right? So distributed caching is also really useful for presenting what we call cache stampedes. So a cache stampede is when a non-distributed cache fails. So when you've got 10 web servers and they all store some data locally that they get from a database, right? And when they go offline and come back, when all the cache data would be recalculated by the clients, what would happen is those servers would all come back and they would all run their expensive operation 3 times rather than just once. And only this way, actually, when a request comes in, only one server will do that. It'll put the data in the distributed cache, and only one of the machines will have to recalculate that expensive query. So it really saves you a lot of CPU cycles. Distributed caches are literally everywhere. So all of the major hosting providers tend to support Memcache or Redis compatible memory caches. What that means is you can basically use your npm memcache client library to access them, even if they are secretly some other kind of program. Understanding how distributed cache works is remarkably simple, actually. When an item is added, the key, the thing that you use to retrieve that item from memory that is generated, just includes the address of the computer that's storing the data in memory, right? So generating a key on any one of your machines will always generate that same deterministic key. So that's it. It just means that instead of having to scan through 3 terabytes of memory split across 3 1 terabyte chunks, by putting the address in the cache key, your computer knows which computer to jump to really, really quickly and just grab the piece of data. It's just really fast. Breaking up large pools of shared memory like this is really smart because it makes looking things up so fast, and no one computer needs to scan huge amounts of memory to retrieve an item. Cdns. So I touched on this a little bit earlier because I didn't remember there was a slide about it. So Cdns are just web servers run by other people all over the world. That's all it is. You upload your data to them and they will replicate your data across what they call edges. That's just a silly word that means to all the servers where they run, right? So that when someone requests your content, what happens is the DNS, the domain server, points them to the server closest to them. So then the time it takes for them to fetch the content from the web server is that much quicker. They just distribute your content globally. So the mechanics of operating a CDN are vastly more complicated than just using one, but they're a great choice if you have a lot of static assets like images, or especially big files like videos or large binaries. They're like super useful to reduce the overall load on your servers, because anything that's retrieved from a CDN, you're not actually having to serve from your own hardware. So offloading to a CDN in that way is one of the easiest ways you can get really, really loads of extra performance for like next to no cost. So let's talk about design patterns, because obviously we've all heard about this stuff, and that's like real architecture, right? So like design patterns are literally just bug fixes for your programming language, legitimately. So people will talk about design patterns as if they're some holy grail, but all a design pattern is the answer to a problem that people solve so often that there's an accepted common way to solve it. That's all it is. It's something we wrote down. If our languages, tools, and frameworks were better, they would probably do the job for us. And in fact, newer language features and newer languages and tools often make older design patterns obsolete over time. We're going to just run through some bullet points of some of the really, really common design patterns you'll hear about, and I'll give you like the 1-sentence précis of what it really means. Cool. So MVC, that just means split up your data, model, and UI code along with your business logic so they don't get confused. Cool. ORM, object relational mapping. All this really means is use a mapping library and configured rules to manage the storage of your in-memory objects and save them into a relational database. Don't confuse your objects and where you save them together. It maps the two things. Active record, very, very familiar if you've ever used Ruby. All your objects should be able to save themselves because everything else is just a dumb web form. We don't really care if our objects are tied to our database. They are active records. Repository. All of your data access is in this class. Interact with this class to load things. Decorator. add or wrap decorators around an object. So all that means is wrap one thing in another, like wrapping one function around another. To add common behavior like caching or logging without changing the original implementation. So all of that extra cross-cutting stuff just lives in the decorator. Dependency injection. If your class or function depends on something, it's the responsibility of the caller, normally the framework you're using, to give you that dependency. The factory pattern. Put all the code you need to create one of these things in one place and one place only. The adapter pattern. Use an adapter to bridge the gap between things that wouldn't otherwise work together. What adapters do is they take data in one format and they convert like an external representation from another system, and they turn it into another format. So it's like converting a Twitter API response into my cool social media data structure. That's an adapter. And the command pattern. Each action or request is implemented in a single place. The final two, we've got the strategy pattern, which just says, define multiple ways of doing something that we can swap in and out. And a singleton. There's only one of these things in my entire application. Okay, so this is a very, very non-exhaustive list of some of the pattern jargon that you hear. And there's really nothing special about design patterns. They're basically just the 1990s version of an accepted and popular Stack Overflow answer. So, microservice architectures, oh boy. Microservice architecture is just the third wave of service-oriented design. So where did they come from? And well, I'm in 36 minutes, we're going to start going fast. So in the mid-90s, Com+, which was called Component Services, and SOAP were very, very popular because what they did is they reduced the risk of deploying things by splitting them into small components. And they provided a standard and relatively simple way to talk across process boundaries. So what this did is this led to this popularization of things called 3-tier and n-tier architecture for distributed systems, which just meant lots and lots of different components stacked on top of each other, much like your core functions, but they were running in their own little processes. So n-tier really was a shorthand for split up the data tier, the business logic tier, and the presentation tier. You might notice this sounds very similar to MVC apps. So this worked for some people, but suffered problems because horizontal slices through a system often require changing every single tier to finish a full change, right? So the ripple effect is really bad for reliability. So product vendors then got involved, and SOAP became this complicated and unfashionable thing, which pushed people towards what we called the second wave of SOA, called Guerrilla SOA. So it had a very, very similar design, just without all the ceremony, and reorientated so people did full vertical slices and bought less vendor rubbish. What this did is it led to the proliferation of smaller and more nimble services around the same time as Netflix were promoting this thing they built called Hystrix, which was their platform for latency and fault-tolerant systems. Right. So this third wave of SOA, which was then rebranded as Microservice Architectures by a man called James Lewis and a man called Martin Fowler. And it's very, very popular, but perhaps not very well understood at all. So what microservices are supposed to be is small, independently useful, independently versionable, independently shippable services that execute a specific function or operation in your business. What microservices often have become are brittle, codependent, myopic services that act as data access objects that talk over HTTP. And when one of them fails, all the others around them fail, right? So that's not actually microservices. Those are domino-like nanoservices. So good microservice design follows a few very, very simple rules. You've got to be role or operation based rather than data-centric. So talk about what your service does. They always own their own data, and that doesn't leak out. You should always communicate using external interfaces like APIs or messages rather than integrating at the database. And the golden rule for me is what changes together and is codependent is actually the same thing, right? So don't split your things up into too many small components, because actually a broader logical grouping is often less brittle. Also, all services should be fault tolerant and survive the outages of any other dependency or microservice. Any microservice that doesn't exhibit those qualities is likely just a secret distributed monolith. And that's okay. That's totally okay. Loads of people operate distributed monoliths at web scale, but you will feel some pain of it at some point. Okay, well, how about this? This is real architecture, right? Hexagonal architectures. What? Okay, so the hexagonal architecture is also known as the ports and adapters pattern, which was defined by a man called Alistair Coburn, and is one of the better pieces of real application architecture advice that anyone will ever give you. Put simply, have all of your domain logic and business rules, right? Have them exist in a form that isn't tied to your frameworks or your dependencies or your data storage or your message buses or your repositories or your UI. All of your logic should kind of live on its own, right? In its own little classes and files. And all of that outside stuff is adapted to match your internal model and injected in when required. So what does that really mean, right? It means all your logic is in files, modules, or classes that are free from framework code, that does not reference your framework, any of that glue or database logic, right? Why would we do that? That sounds like a lot of work. Well, what it means is that you can test everything in isolation. You can test everything without your web framework or some broken API getting in the way. It means that it keeps your logic clear from all of those external concerns and is a really safe way to design applications. So there's a second quite popular approach described as 12-factor apps, which mostly shares these same design goals. And there's a few more prescriptive rules thrown on top. So scaling is another topic that comes up all the time. And scaling is really hard if you try and do it yourself. So absolutely do not try and do it yourself, right? Super simple. Use vendor-provided cloud abstractions like Google App Engine, Azure Web Apps, AWS Lambda, anything with auto-scaling support enabled if you can possibly do it, right? Consider putting your APIs on a serverless stack. The further up the abstraction you get, the easier scaling is going to be. So conventional wisdom says that scaling out is the only cost-effective thing, but you know what? There are plenty of successful companies that have managed to scale up with only a handful of large machines or VMs, Stack Overflow being the most notable one. It's like 8 web servers and a database. Scaling out gives you other benefits, often geographic distribution related or cross-availability zone resilience, but don't feel bad if the only lever you have is the one labeled more power. That's totally fine. So building distributed systems is even harder still than building just one app. And nobody really talks about that much, but it really is. It's much easier for something to fail when you split everything up into tiny little pieces, but you're less likely to go completely down if you get it right. There are a couple of things that are always useful, right? So you want to make sure you use like circuit breakers everywhere. So circuit breaking is a pattern where you model any of your outgoing connections like they're an electrical circuit. By measuring the success of calls over any given circuit, if calls start failing, you proverbially blow the fuse and end up queuing all of your outbound requests rather than sending requests that you know will fail. So after a little while, you let a single request flow through the circuit. We call this half open. And if it succeeds, you close the circuit again and let everything that was queued flow through. Circuit breakers are like this phenomenal way to make sure that you don't fail when you know it's possible. And they also protect the service downstream from being pummeled into oblivion by a load of calls. You'll be even more thankful for your circuit breakers when you realize actually now those downstream APIs are also owned by you. Idempotency, great word, and retries. So the complementary design pattern for your circuit breakers is that you need to make sure that you wrap all outbound connections in a retry policy, along with a backoff. What this means is you should design your calls to be non-destructive. So if a call comes in twice, nothing bad happens in your system. The same effect happens. That's what we call idempotency, again, jargon. And that if you have calls that are configured to retry on errors, that perhaps you back off a little, if not exponentially, when repeated failures occur. So at the very least, to give the thing you're calling time to recover, it just kind of means that you retry it 30 seconds, 1 minute and a half, 5 minutes, 10 minutes, 30 minutes, and 1 hour, rather than every 10 seconds, because that will just pummel the server into the ground. Bulkheads. This is something that's inspired by physical bulkheads in submarines. So when part of a submarine's hull is compromised, the bulkhead's shut, preventing the rest of the submarine from flooding. It's a pretty cool analogy, and it's all about isolation. So reserved resources, so capacity or physical hardware, can be protected for pieces of your software so that an outage in one part of your system doesn't ripple down to another. You can kind of set like maximum concurrency limits for different parts of your system, and that's what bulkheading means. And event-driven architectures with replay and message logs. So these are cool because by design, inbound calls are made to them and are not synchronous by design. So by using events that are buffered in queues, your system can support outages, scaling up and scaling down, along with rolling upgrades without any special consideration. It's like a really normal mode of operation to read from a queue. So whether you're doing that to recover or whether you're just doing that to process regular data, it's the same thing. So you can combine it with like multiple nodes all trying to consume from the queue at one time to scale out really, really quickly. So it's a classic ticket sales design pattern. So do you need Kubernetes for all of this, right? No, you probably don't have the same kind of scaling problems that Google does, right? This is really, really important. So with the popularization of Docker and containers, there's a lot of hype that's gone into things that provide almost platform-like abstractions over infrastructure as a service. And these are all very expensive and hard work. If you can in any way manage it, use the closest thing to a pure managed platform as you possibly can, right? So app services, App Engine, Lambda will be several orders of magnitude more productive for you as a programmer. They'll be easier to operate in production. They'll be more explicable, more supported. Kubernetes, often irritatingly abbreviated to K8S, along with its wonderful ecosystem of esoterically named add-ons like Helm and Flux, basically require a full-time ops team to operate, even when you're in managed vendor mode using EKS, AKS, GKS on the cloud platforms. That learning curve is really steep, way steeper than the alternatives. Heroku, app services, App Engine, those are the things that you'll be able to set up yourself in production in minutes rather than weeks. And then to close us out, I want to just mention one thing about cloud neutrality. So you'll see a lot of pressure to push towards cloud neutral solutions using Kubernetes in various places, but it's all snake oil. Being cloud neutral simply means that you pay the cost of a cloud migration, which is maintaining abstractions that isolate you away from useful new features all the time, rather than in the exceptionally unlikely scenario that you're going to switch cloud vendor. The responsible use of technology includes using the thing most suited to the problem and the scale that you have. So architecture really isn't so hard. We should always do the simplest thing that could possibly work. It has a cost, just like every abstraction. And we need to be sure that we're getting the benefit before you dive into some of the more complex architectural patterns. Most often, and the thing that's dearest to my heart, is the best software architectures in the world are the simplest and the ones that are most easy to change. Architecture isn't really difficult if you don't let it be. And that's me, 47 minutes. I do hope I haven't run over. Let me stop sharing my screen. And I think you can probably all see my face now. Amazing. Does anyone have any questions? I appreciate that was like a huge amount of information in a very, very short period of time.